This is problem 1039. It says we have a hollow thin-walled sphere of mass 12 kilograms and diameter 48 centimeters. It's rotating around an axle through its center. The angle and radius through which turns is a function of time in seconds given by theta equals a t squared plus b t to the fourth, actually. So put that down. Where a has some numerical value, 1.5. B has a numerical value, 1.1. Okay, the first one is, what are the units for the values of 1.5 and for the constants A and B? Well, all you have to do is think about the units for theta are radians. And so we have the units for A and the units for T are seconds. So we have seconds squared, so the units associated with constant A are just going to be radians per second squared, and also consequence B is going to have units of radians per second to the fourth. The radians really don't have any units, but I think we would include radians, so we'll see what happens when we look at the answer. But I think that's what I think they should be. Then it says, what are the units? Okay, what at the time 3 seconds, find the angular momentum of the sphere. So the angular momentum for an object, which I think we call J, is equal to the moment of inertia times omega. So we can calculate the moment of inertia from our formula that we get out of the book, 2/3 m, which is 12 kilograms, times r squared. The diameter is 48, so r is 24 centimeters. We'll make sure that convert that to meters, so we get 0.24 meters. So we get 0.24 meters squared. And so our moment of inertia is 2 divided by 3 times 12 times 0.24 squared, and we get 0.461 kilograms meters squared. Okay. The omega we do by taking the derivative. So omega is just d theta dt. So if we take the derivative, we'll get 2at plus 4bt cubed. So omega for 3 seconds, we'll get 2 times a, which is, what is a equal to? I'll write that down somewhere, didn't we? Okay, it's in the book. It's 1.5. So 1.5, the units for A are radians per second squared. We multiply by 3 seconds. That'll give us radians per second. So that's good. Then we have 4 times B, which is 1.1 units of radians per second to the 4th power times 3.00 seconds to the 3rd power. And again, you see the units work out because we have radians per second to the 4th multiplied by seconds cubed, you get radians per second. So we get 2 times 1.5 times 3, that's the first term, plus 4 times 1.1 times 3 to the 3rd power. So I get 128 radians per second. Now to calculate the torque, we use Newton's second law, which says the sum of the torques is equal to the moment of inertia times alpha. So all we have to do is, we already have the moment of inertia, we just have to calculate alpha. But alpha is just d omega of t dt. So we take the derivative of this expression, and we'll get 2a plus 12b t squared. So that's alpha. So we can evaluate alpha at 3 seconds. So we get 2 times 1.50 radians per second squared, so that has the right units. And then we have 12 times b, which is 1.10 radians per second to the fourth, times 3.00 seconds squared. Again, we get radians per second squared, so multiply that up, we get 2 times 1.5 plus 12 times 1.1 times 3 squared, and I get that alpha is 122 radians per second squared. So our torque, our net torque applied is going to be the moment of inertia, which is 0.461 kilograms meters squared times alpha, which is 122 radians per second squared, and plug it into the calculator. We get 56.1 Newton meters. Those are the units for torque. Okay, so that was, what number was that? That was 1039. Let's go look in the back of the book. 1039. Okay, A has units radians per second squared, B radians per second to the fourth. The velocity, or angular velocity, is, well, they have radians per second. What are they doing here? They have kilograms meter per second squared. That sounds like a force. I got the second part right. Maybe I read the problem incorrectly. Kilogram meter per second, meter squared per second. Oh, no. So omega, did I actually calculate? I never did calculate the angular momentum. That was my problem here. So I got the third part right. The angular momentum is J, and that's equal to the moment of inertia, which is 0.431, I think, 461. 0.461. The units of that are kilograms meters squared, multiplied by omega, which is 128 radians per second. Okay, that's all working out now. So J is that product, 0.461 times 128, which is 59. So I get 59.0. The units are kilograms meters squared per second. We drop the radians when we get with the moment of inertia. So it's 59. Yeah, that's right. Okay, so that's the angular momentum. I never did calculate. And then the torque is 56.1 newtons meters. So it's just like the linear problems where we were given a polynomial and we had to take the derivatives to find the velocity and acceleration. Here we're taking the derivative of theta as a function of time to get omega, and taking the derivative omega to get alpha. And then we're using Newton's second law to calculate the torque. Then that torque that would cause that to happen.